SwayamPrabha. Digital India. Educated India.
Dear learners, greetings from IIT Guwahati. We are in the MOOCs course Power Plant System Engineering Module 4, that is Hydro and Renewable Energy Generation Systems. So, in our last lecture we are focusing on wind energy part 1. Now, in continuation of this wind energy, we are going to discuss some new concepts of harnessing wind energy. So, in our previous lectures, I emphasized about the harnessing wind power in a typical propeller driven wind turbines, and it is mainly governed through steady flow energy equations, or in turn Bernoulli's theorem can be applied everywhere in the flow field except the location at which the energy is being harnessed by the turbine. Now, similar concepts can be extended for other types of turbines to have a better design of those kind of innovative wind turbine blades for localized power, or where the velocity of the winds are relatively less. Then we need to think about the governing aerodynamics principles of it. So, for that reasons we are going to introduce a topic which is called as Magnus effect, that which is a kind of aerodynamic principles which is being used for innovative designs of wind turbine blades. In fact, Magnus effects is a kind of a situation that where if you are able to rotate a cylinder in a free stream medium, it says that the pressure difference across this cylinder surface will create a lift. So, essentially in other words, if you design our blades in such a way that irrespective of the direction of the wind, if you can ensure a lift force, then we will be able to rotate the cylinder. So, that is the basic philosophy or fluid mechanics principles, or in fact aerodynamics principles behind the vertical axis wind turbines, and which we are going to discuss now. Then we will, based on these two concepts like Bernoulli's theorem and Magnus effects, the entire wind turbine family is being classified and we call them as wind machines. And lastly, I will just try to emphasize, when you install a wind turbine at a particular locations, it is expected that it should cater the based on the uniform speed or that locations, it should be able to perform it will be able to perform the in a manner that the total rated capacity of the power can be generated. So, I will give a brief introduction on these topics. Now, let us start just brief introductions. Like in our last class I mentioned that wind has immense potentials. It falls under the roof of renewable energy. Apart from solar energy, hydro, geothermal, bio, wind also has a definite potentials for harnessing power, and it is treated as a renewables, and since it has been a kind of a energy resources which is being projected as a major source of power by end of 2050. So, lot of studies has been put, a lot of research has been put on these topics. However, in our study we will just focus on some basic aspects of this wind. So, in our last lecture we have discussed about a propeller driven or horizontal axis wind turbines, where we say that the turbine is installed in a manner that direction of the wind and axis of this rotation, they are parallel to each other. So, in other words, wind directions and the horizontal axis are in parallel. So, based on our analysis, we have imagined as if there is a stream tube which passes through the propeller, and wind has its initial velocity or which enters into this stream tube and leaves at some exit pressure and velocity. So, through this process we apply Bernoulli's equations at two locations, that means at a free stream, second at the location at which the turbine is mounted, that is between A and B. So, Bernoulli's equations is applied between I and A and further between A, B and E. So, that way we can see there is a increase in the pressure, and when the stream approaches the turbine, again from when the flow leaves the turbine, there is also increase in the pressures. So, what happens in between? So, this is the zone where entire kinetic energy of the flow is being taken by this rotor or that propeller. So, that way the pressure drops from PA to PB, and also that point of time we have bring back this velocity BI to this BE velocity at these locations. So, what we have seen here is that through this analysis we have defined the term what is the total power that is available in the wind, and through this particular arrangement what is the maximum power that we can extract, and difference between them gives rise to the maximum power coefficients. And these maximum power coefficients you can see here, it is independent of any kind of wind turbines blades or independent of materials or independent of the wind velocity and all. So, that is the reason we put this maximum power coefficient as a what is called as Bayes number, and that number happens to be 0.593, and the Bayes limits indicates that maximum power can be extracted from wind is independent on the design in an open flow environment, because it is a fixed number. So, that way one can plot the power coefficients as a function of tip speed ratio. But what happens here is that when you install a particular turbine at a given locations, it depends on three major factors. One is what is the maximum swept area or capture area that we can achieve. So, that is achieved through the rotor area or wind turbine area, and which is defined by its radius r, and the omega which represents that with given wind speed velocity of V I, what is the rotation of the turbine that we can achieve, that is angular velocity. So, considering all three numbers, we define a term called as tip speed ratio, and this tip speed ratio is for any given turbines has certain limits of its operation in the tip speed ratio. So, for that reasons there are different class of turbines as you can see in the figure, like multi-blade type, maybe we can say 4-arm type, Darius types, horizontal axis types, and we can see that they have some limits in which they operate in a particular tip speed ratio. Now, having said this, and on top of that we have this, whereas if you look at ideal propeller type turbine, it is independent of all these internal designs. So, it is that efficiency initially increasing and it keeps on, it becomes a fixed value, and that at this number 0.593. So, all other turbines that operate always below that number. So, that is the reason we say it is a Bayes limits. So, in other words, what we can say, wind has a potential to work up to the Bayes number, but in a given wind turbine at a particular geographical locations, it is not possible to reach that number. So, that is what we have different ways that how we can achieve, and if ways to design the blades of the wind turbine to achieve this. So, one way we have understood the fact that a typical horizontal axis wind turbine, which is normally fall under the category of propeller driven turbine, they have their own limitations, because they operate in this tip speed ratio between 4 to let us say 7. but there are some other possibilities. Can you design any other kind of turbines which can also work at low wind speeds? So, to answer these questions, then we have to look into some other options or other designs. So, obviously, when you move on to other kind of designs, the concept that we apply for propeller type may not fit. So, for that reasons we have to find out some other principles. And second reason is that when you look at the high speed horizontal axis wind turbines, they are generally operated at wind speed of more than 100 kilowatt or above. Now, if the wind speed is still there, if in a particular locations that if we have wind is available, but it is not, we do not have possibility of installing such a big capacity turbines. So, can we think of having installing a small capacity turbines which will incur less structural stability, which because horizontal axis wind turbines are very prone for axial thrust, and because they operate at higher wind speeds. So, for that reasons we have to go for some other alternative solutions. So, that is where this Magnus effect comes into pictures. So, this Magnus effect is a typical aerodynamic principles which says that we can think of a lift based wind turbines rather than conventional propeller wind turbines. So, what is that lift based wind turbines? Because they are governed by this Magnus effects. Now, what is the advantage of those turbines? Because they can be useful or they can be considered as novel small wind turbine novel designs, and the power generation may be less than 100 kilowatts. So, they operate at low wind speeds and they fall under category of rotor type, one like Savonius rotor, Darius rotors. Okay. So, those turbines we can design those blades, and that blade should be lift based designs. That means, if you are forcibly from the wind speed at a given locations, if there is a wind available at certain speed, through that speed if you can design some turbine blades which can generate lift on those designs, then obviously the system will rotate or this rotor will rotate. So, this is what exactly Magnus effects talks about. So, for the time being, let us not talk about the turbine itself, rather we will just talk about what is this Magnus effect tells us, what inference we get the Magnus effects. So, the Magnus effect demonstrates that a lift force is generated if a horizontal cylinder is rotated about its axis and moves through the still wind. Conversely, if a stationary horizontal cylinder is rotated about its axis in a crosswind, it will generate a lift force. So, in other words, that we will try to see this Magnus effect in a this is what about the horizontal cylinder. Now, this Magnus effect we will try to see if it happens to be a vertical cylinders. So, effect is equally applicable to a vertical cylinders when it is rotated about an axis in a crosswinds. So, it will experience a force perpendicular to its axis, which will cause it to move in the direction perpendicular to the wind. So, in other words, we can think of a vertical cylinder if it is placed in a crosswind and we are able to generate a lift, then obviously the cylinder will rotate. So, this is what exactly we want in a vertical axis wind turbine. Another thing is that to make this analysis more simplified, we can imagine this length of the cylinder to be much greater than its diameter, so that the flow around it can be considered typically to be two dimensional, because length effect will not come into picture. So, we will discuss this Magnus effect in details. So, to demonstrate this Magnus effects, we will try to see first consider simple aerodynamic principles in which we take a non-rotating vertical cylinder which is placed in a non-viscous flow. So, ideally it is a non-inviscid flow, and when you put it, this is what we look at, this is a vertical cylinder placed in an inviscid flow. What we expect is when it is placed in a uniform stream, we will find the streamlines approaching in this manner, and typically the the streamlines will from upper and lower part of the cylinder will be symmetrical in nature. What we see here, that when the flow approaches the cylinder, flow approaches to the cylinder, all the streamlines will be symmetrical about its axis. So, what we think is that we can say the cylinder geometry is defined by this angle theta, radius is defined by this r, and any from the center we define a radius r which is small r at any location downstream, because where this r is always greater than capital R. So, now if you want to find out the velocity at any point on the surface, we can draw a tangent. So, we will have a velocity v theta, and that will define its velocity. Now, once you know this velocity, we can also apply Bernoulli's equation to find out the pressure. So, there are two locations, one is location I and other is at location theta. Theta means on the surface. So, we apply this Bernoulli's equations by neglecting potential energy effects. So, two locations we apply to find its pressure, but velocity on the surface can be defined as twice time V I sin theta, that is from this equations on the surface, that is what we call as V theta directions. Now, once we know this theta, we can also define non-dimensional pressures, because this what remains constant is the half rho V infinity square, V by V I square. So, this term is called as dynamic pressure, and for a given wind velocity, this dynamic pressure is a fixed quantity. So, a non-dimensional pressure can be defined, which is nothing but the pressure difference between at any point on the surface and the free stream pressure divided by this dynamic pressures, and it happens to be the fact that P star theta becomes 1 minus 4 sin square theta. So, a close look on this analysis, we can see that it is quite obvious that when velocity is low, pressure is higher, velocity is more, pressure is lower. So, obviously from this analysis we will have stagnation points at two locations, for which one is at theta is equal to 0, other is at theta is equal to 180 degree. So, at this location theta is equal to 0 degree, at this location theta is equal to 180 degree. So, we have the stagnation point. Stagnation point is means this velocity, flow velocity becomes on the surface becomes 0. So, when we have velocity becomes 0, at that point pressure is happens to be maximum. Now, so that way we can say that at stagnation point your P star theta is equal to 1 and velocity is 0. Now, moving on to these things, and if you take a kind of a streamlines and velocity distribution pattern for this horizontal cylinder, if you can find, we will have for a given velocity V I, we will see that there will be a uniform pattern of pressures, velocity on this entire surface of this cylinder along its axis, when the flow pattern is symmetric about this axis. And since the flow pattern is symmetric in axis, so obviously what conclusion that we can draw is that there is no resultant force either parallel or perpendicular to the undisturbed streams. Hence, there is no drag or on the cylinder, or there is no lift force. So, the drag and lift is nothing but the term that are used in aerodynamic term, any force which acts perpendicular to the free stream direction of the flow, like here it is the wind speed, is the lift, and any force that acts in the opposite to the direction of the wind speed is the drag. So, obviously drag and lift, they are perpendicular to each other, and we will use the same term for analysis of this Magnus effect. So, what we see here is that streamline patterns and pressure distribution pattern for a non-viscous flow past a non-rotating cylinders. Now, let us move to the next effect, and this is instead of keeping this cylinder non-rotating, you start rotating the cylinder at certain velocity, but keep this air stream as stationary. It means you are just rotating a cylinder in a ambient air, stationary air. there is no air velocity or free stream velocity. So, that way if the effect will be a that means you are inducing a circulatory flow around a rotating cylinder. That means, so through these rotations the air also feels the effect of some circulating actions due to these rotations. Of course, the effect is more predominant in the vicinity of the cylinders, but far away from this cylinder we have still we have free stream velocity V I, pressure P I, and far away from this side also free stream pressure and free stream velocity remains same. So, that means far stream is not affected, but the vicinity of the cylinder gets affected through this rotation of the cylinder. So, here what we observe here is that the rotation of the cylinder produces circulatory flow around it, but air far away from the stream is still at rest. Now, when we say that air then what velocity it rotates? To do that, it can be shown that the velocity is inversely proportional to the distance from the cylinder axis, and for which we can put a dimensional constant, and that dimensional constant is termed as the circulation. So, if you say this radius of the cylinder is r and any locations which is small r beyond this cylinder radius, we can find out the velocity in two parts. One is the cylinder peripheral velocity, that is V p, other is velocity at any distance r from this axis, so that is V r. And typically peripheral velocity is a constant quantity, and we term this as circulation, and that is also equal to twice pi r into V r. Now, from this actually if for a given wind speed, if it rotates, if it makes number of revolutions, so we can multiply n into it, where n stands as number of revolutions per unit time. So, accordingly we can have the circulation constant as twice pi r square into n. So, here what we observe that when a cylinder rotates in a still air, it produces a circulating effect or flow around the cylinder. Now, we merge this or superimpose these two effects. So, first thing, non-rotating flow in a uniform stream of air and rotating flow in a still air. So, we have analyzed both the things separately. We have V theta here, and here we have circulation here, and when you superimpose these two things, we will have a net effect which is nothing but we call it as a rotating cylinder in a stream of air. So, when we have a rotating cylinder, that is a stream of flow, then we have these effects, and there we can have both the effects together, and this velocity on the surface can be defined at any location theta as two parts. One is V theta, other is V p. V p stands as this peripheral velocity, and this peripheral velocity is a fixed quantity, that is circulation by twice pi r. So, that way the most significant effect that we can observe here, that the observe here is non-uniform pressure and velocity on the upper part and lower part of the cylinders. So, if you look at this particular figure here, in this case the streamlines have uniform pattern and there is a flow symmetry. Here also we have flow symmetry about this axis, but here it is a non-symmetric. By non-symmetric means we will have a different values of pressure distribution and velocity pattern. So, what does this mean? In this case we have two stagnation points, let me put as A and B, which we have already defined, and second, here we will not have a stagnation point because it is cylinder is continuously rotating. Now, when these two effects will be merged, then what may happen is that there will be two situations. One, if you take as upper part of the cylinder and lower part. Now, the upper part of surface of the cylinder will experience a higher velocity because the velocity gets added, whereas the lower part of the cylinder will be at lower velocity because the velocity is in, they oppose the directions. So, the combined velocity pattern will show that they will reinforce in the same directions, that is in the top, and they will oppose each other in the bottom. So, net effect is to increase the velocity at the top and decrease the velocity at the bottom. So, net effect would be that initially which was there were two stagnation points at this point and this point. For a symmetric case, they will try to move towards each other. That means, point A and B will move towards each other, and we will have a stagnation point at maybe at point C, and that is nothing but that we will see at theta is equal to minus 90 degree. And from this analysis we can say that why the simple calculations, why we say that velocity will be higher in the top, because this expression will say that sin theta will be positive between theta is equal to 0 to 180 degree, and for the bottom surface theta is equal to 0 to minus 180 degree, sin theta is negative. So, this gives the fact that net velocity increase in the top surface, there will be decrease in the velocity in the bottom surface. So, the other side of the effect of this velocity is that the pressure of the cylinder will be higher in the bottom and lower on the top. Now, through this process what we arrive at here, that there is a pressure difference, and there is a pressure difference between top and the bottom surface, and this pressure difference will give you a upward force, and this upward force is known as lift force. So, what we can conclude from this Magnus effect analysis is that when a rotating cylinder is placed in a stream of air, the higher pressure there is felt on the bottom surface, and it induces an upward force, and this upward force acts in the direction perpendicular to the stream directions, and this upward force is known as lift force. And this lift force is nothing but the combined effect of what we say integrating the pressure over the projected area. So, in net effect of the pressure difference multiplied by area will give you the force, and this pressure anyway we are going to calculate through this Bernoulli's equations. So, that way what is our analysis that we are going to see here? We are going to find out or use this Bernoulli's equation at two locations. One, any point on the surface which is defined by this angle theta. So, we say p theta and b theta, and here any location we say pi bi. So, these equations are applied here. So, we find b at any point on the surface, and we know that what is b, because it is a rotating cylinder in a stream of air. So, b is equal to twice bi sin theta plus circulation by twice pi r, your addition this circulation velocity Vp and velocity on the surface b theta. So, by putting this velocity term in this pressure equations, we have the pressure on the surface of the cylinders, and when we integrate this pressure over this frontal area, and this frontal area or we say projected area, if you look at take this as projections of the cylinder to find out the projected area, we will have a rectangle. For this rectangle you have your length has 2r, and this is h. H is nothing but your this will have 2r length, and this height with respect to cylinder, this is height or length of the cylinder. So, this projected area becomes twice r into h. So, when you put this we form an equations that lift force Fl becomes equal to twice pi rho r h Vp into Vi. So, Vp is your peripheral velocity, Vi is your incoming free stream velocity. Peripheral velocity can be related to twice pi r n, n stands as the number of revolutions it is making. Then by putting this it becomes now 4 pi r square rho r square h into n into Vi. This is one way we find the lift force by integrating pressure over the surface of the cylinder. Now, there are other ways that lift force can be expressed in the form of lift coefficient, that is CL. That means, in general lift force is defined by CL times A into its dynamic pressures. So, by combining these two we get a term which is called as lift coefficients. CL is equal to twice pi Vp by Vi. So, here important point to be noted here, if we have Vi velocity here in the free stream, but when it approaches we have a Vp velocity which is on the surface. So, it is Vp at this point. So, that is circumferential velocity, sorry. So, this is the circumferential velocity on this surface, and the CL is basically function of Vp by Vi, and this Vp by Vi is known as velocity ratio. At the same time, we also have half rho Vi square term, and we call this as a dynamic pressures. Now, this entire analysis shows that the pressure is non-uniform on the surface. So, as a result we will have a non-uniform pattern in which your P star which is non-dimensional pressure will be different at different locations. So, this non-uniformity of this velocity and pressure distribution and streamlines pattern is shown here, and it is for the case of non-rotating cylinder placed in a viscous flow. So, this is a case where we can say that there will be pressure and velocity non-uniformity on the surface. Now, moving further, what we have done so far, a idealistic theory, and that is called as ideal non-viscous flow, for which we take this, find the lift force, and this lift force we say, or lift coefficient is defined by twice pi into Vp by Vi, and it happens to the fact if Vp is equal to Vi, CL becomes a fixed number. So, this is where the ideal theory is all about, but in reality this is not the case, because there are issues like effect of viscosity, boundary layer separations that makes the flow in non-uniform pressure distributions. So, obviously we will not try to use this ideal theory for a realistic applications, and if it happens to be for wind turbine design, then we have to be more realistic number or careful. So, for that reasons we define the term Reynolds number rho V Vi d divided by mu. So, Reynolds number is defined for the flow which is available in the free stream, which is a combined effect of the wind velocity, and if you harness this flow through a diameter d and mu is stands as a viscosity, then we can calculate what is this Reynolds number Re for the flow, and for a given Reynolds number we can plot various values of velocity ratio with respect to lift coefficients, and in fact these are what we call as experimental observations or experimental trends. So, their trends are depends on two factors. One is what is L by D, that is lift to drag ratio, and if they are becomes higher and higher, that means lift is much higher than the drag, or lift to drag is a kind of a fixed number, lift is almost 2 times of drag for a given Reynolds number case. So, that way one can say what will be the upper limit of this lift coefficients. So, for an ideal theory, lift to drag ratio when it goes to infinity, so it will lift to CL will keep on increasing, but that is not the trend. But realistic number, if you can say for a particular velocity number, this much difference we can get. So, for example, at velocity ratio of 2, the ideal theory will give predictive lift coefficient of 12, but your experimental evidence will show lift coefficient something close to maybe 4.5. So, that much difference comes into picture when for a non-uniform pressure distribution case, that when you do the analysis for a realistic flow. So, that is the reasons we normally take the data from the experimental evidence for wind turbine calculations, and that is dependent on this velocity ratio. Now, having said this lift force, we will try to introduce another term which is called as a drag. Drag is nothing but the force that acts in the direction of the stream. So, in other words, when we say that when a rotating cylinder is placed in a stream of air, the drag force is the force in the direction of the stream. Now, here in this particular case, your drag force will be 0 because the Magnus force does not gives the indication of the drag force, because when you say velocity pattern and pressure distribution in the direction of the stream. But in general way we say this drag force F d is equal to C d times A half rho V I square, and essentially this drag force is also a function of Reynolds number. So, in a ideal theory we have non-uniform pressure distributions. So, of course, when we have a lift force in an ideal theory, there is a lift force, that is C L is equal to 2 pi when V p is equal to V I, and for that case your drag force will be 0. That is the prediction from the ideal theory. But in realistic case, when there is a non-uniform pressure difference, then we will find that still there will be a drag force. That is the reason what we call this for real fluid. The pressure imbalance results a drag force in the direction of free stream. So, that is a function of again Reynolds numbers. So, essentially both lift and drags, the coefficient, they are function of Reynolds number, and that has to be found out from the experimental observations. So, a typical trend is shown here, where we present the drag coefficient C d as a function of Reynolds number, and in more analysis, when the Reynolds number is much higher in the order of 10 to the power 5 to 6, so this is a closed number of C d approximately 0.4. So, this is all about the drag force. Knowing all these lift and drag force concepts, we are now in a position to define various designs of wind machines. So, wind machines fall under the category that they are typically conventional machines which captures wind kinetic energy and converts it to power or mechanical work. So, we have shown two fluid mechanics principles, one is through Bernoulli's theorem, other is through Magnus effects, how we can harness power from wind by using these machines. Typically, we call them wind machines are commonly known as wind turbines, because these machines produce power. So, whatever produce power we call them as a turbines. So, specifically we call them as wind turbines, and they are classified in 4 major category: axis of the rotation, installation side, operation scheme and aerodynamic force. So, axis of rotation we have put at 2 category: horizontal axis wind turbine, vertical axis wind turbine. Based on aerodynamic force, which is the other extreme, one is called as a drag based turbines, one other is lift based turbine, other is the combined. Now, other part of this, that means for commercial point of view, we call this as installation side. So, you can have offshore turbine or onshore turbine, that means turbines are close to, some turbines can be put at close to sea, other is from far away from the sea. Now, operation scheme, it can be thought of having a fixed pitch control type or variable pitch control type. Other main important aspect is rotor diameter and power rating. So, rotor diameter and power rating, they are fall under different groups from micro to large scales, and typically when you go from large scale type, we take care about, that is taken care by horizontal axis wind turbines, but when you go for lower side, this is taken care by vertical axis wind turbines. But under that roof there are multiple ways we can go for innovative designs, but each of them has their own advantage and disadvantage. For example, when you say horizontal axis wind turbines, they are very good for more power generation, more than 100 kilowatts, but they require a very safe structural side because they operate at higher wind speed. So, obviously, they are very prone for stability of the structure. And again at a given locations there are possibilities wind may not flow in a particular directions, but whereas the horizontal axis wind turbines are very prone to the direction of the wind. So, you have to find the wind locations, otherwise it will give a detrimental effect. But whereas the vertical axis wind turbines, their direction can be changed from the based on the direction of the wind because of their geometric features. So, in a horizontal axis wind turbine, the axis is perpendicular to this plane, and in a vertical axis wind turbine, if you can see this design, so wind directions keeps on changing from the entire surface. So, for horizontal wind turbines we call them as a rotor, upwind rotor, downwind rotor. Vertical axis we call as a Savonius, Darius and gyro mills. Apart from this there are many other kind of things. We have multi-rotor, four-arm rotor, but many other designs, and most important fact is that each of the designs they have a limitations of different tip speed ratio. So, for a given wind speed we require a fixed tip speed ratio. So, this is all about what is the basic difference, because each horizontal axis and vertical axis wind turbine they have their own merits and demerits. And ultimately in the finally if you classify the wind machines based on this horizontal and vertical axis type, we have this particular slide shows that most economical and power turbines that can harness wind power as of now is of this type, and moreover all lift based turbines they are based on Magnus effects, and all drag based wind turbines they are based on the Bernoulli's theorem from our in a basic fluid mechanics or aerodynamics point of view. And last part that we want to focus on is that when you think about horizontal or vertical wind turbines, we have shown this particular classical figures which says the power coefficient as a function of tip speed ratio, and each of these designs of these wind turbines have their limitations in their tip speed ratio. And why we say like this? Because when you go for power generation viewpoint, we expect that the turbine should operate in a smooth manner, and we have seen here that the power is function of density, area and V by to the power q, and the maximum the axial force is a function of diameter and V I square, which means any fluctuation in the velocity will have a detrimental effect in the power, as well as it will also have detrimental effect on the axial thrust which denotes about the stability of the structure. So, it means that for wind turbine operations we have a very narrow band of or narrow range of wind speed in which we should operate. So, that is the reason this power and velocity curve has a characteristics curve we normally plot. What we define is a cut in velocity and cut out velocity. So, cut in and velocity and cut out velocity is nothing but your range of V I at a given locations. So, if this V I range that fluctuates at a given locations and it keeps on fluctuating and over the in a day, in a month as well as in a year. So, for based on this we find and we mean wind velocity at that particular locations. So, from this we drop another vertical which we call as V bar, which is nothing but average wind velocity. So, it means that irrespective of the availability of wind speed much above than V I, but we put our rating of the wind turbines in a range and in this range, and we call this as a flat rating. That means, the turbine should operate within that range for continuous supply of power irrespective of fluctuation in the wind speed. So, this is the summary of this wind turbine operations. The cost effective method to design a windmill is to produce rated power less than maximum prevailing wind velocity using smaller turbines and generator unit. So, a flat rating is defined for any turbine machines machine assembly that produces constant output at all wind speeds. Since there is a loss in efficiency and power at low velocity, wind turbine is designed to operate at a minimum wind speed. And then we define which is known as cut-in velocity, and in order to protect the wind turbine wheel against damage at high wind velocity, we also put up the upper limit which is called as a cut-out velocity. So, through this cut-in and cut-out velocity, we should be able to produce wind power continuously. So, the wind turbine must have a capability to operate at variable loads over a narrow range to deliver a constant power. So, you have to operate at various wind speed loads, but to give a constant power. So, this is the entire summary of irrespective of what turbine we are going to use. So, now we will move on to the last point, that is solving the numerical problems whatever we have discussed so far. So, the problem statement goes like this: the average wind flow in a certain geographical location is 13 meter per second and standard atmosphere. We need to find out lift force, drag force and resultant force. So, using a 1.8 meter diameter and 90 meter long smooth cylinder that rotates 140 rpm in the wind speed. So, the problem statement is simple, but here to get this lift drag forces we need to rely on this classical graphs, lift coefficient and drag coefficients as a function of Reynolds number and velocity ratio. So, how do you go about this? So, solution, for the solution, first thing that you see, it is a standard atmospheric pressure, P is equal to 1 atmosphere and T is equal to 15 degree centigrades, that is 288 Kelvin, and this will give you rho is equal to P by RT. R stands as 287 joule per kg Kelvin. So, we can find out what is density of air, that is 1.23 kg per meter cube. And at this pressure and temperatures we can refer data table to find the viscosity of air, and it is average value is 19.7 into 10 to the power minus 6 Newton second per meter squares. Now, with this data we will be able to solve these problems. So, first thing we need to find out Vp, that is peripheral velocity, twice pi r into n, and d is in this case is 1.8 meter and n is 140 rpm. So, through this we can get Vp as 13.2 meter per second. We have been given Vi as 13 meter per second. So, you can see that almost Vp by Vi ratio approximately 1. Now, for this case, what is Reynolds number? Rho Vi d by mu. So, density is known 1.23, Vi is 13, diameter is 1.8, mu as 19.67 into 10 to the power minus 6. So, this is 1.46 into 10 to the power 6. So, we have all the things, and of course, another term dynamic pressure Q infinity half rho Vi square, that is half 1.2 into 13 square. So, this number is 104 Newton per meter square. So, let us go to the basic expressions. Lift force Fl is equal to Cl times A into half rho V I square, and A stands as the projected area, that is twice R times H, and this is 162 meter square. So, to find Cl we require this graph for velocity ratio close to 1, and if you take an experimental observation graph, and somewhere we have to take this middle plot, because that plot fits closely to our Reynolds number value. So, at this location if you drop it, so this number is close to 1, means approximately we can say CL is can be approximated as 1, and then we can write this is 1 into area is 162 into 104. So, FL stands as 16848 Newton, and this drag force FD CD times A half rho BI square. Now, for Reynolds number in the range of 6, if you go and take this particular graphs, the CD is close to let us say 0.4. So, we can say CD is equal to 0.4. So, this number now comes down to FD is will be equal to 6739 Newton. So, resultant force F is equal to square root of FD square plus FL square, and this number is 18146 Newton, and resultant force make an angle phi is equal to tan inverse FD by FL, that is close to 21 degree with respect to wind direction. Okay. So, we have lift force, drag force and resultant force, but however, the theoretical value of lift, or you can say FD theoretical value of drag is 0, FL theoretical would be twice pi times, because Vp by Vi is equal to Vp by Vl 1 implies Cl will be twice pi. So, this twice pi multiplied by 162 into 104. So, FL theoretical value would be 105,860 Newton. So, what I understood here, we understood here your realistic object, that is cylinder, experience 16848 Newton, but actually FL theoretical value would be 105,860 Newton. Correspondingly, FD experimentally is 6439 Newton, but FD theory is 0. So, the net effect is that the ideal theory does not give the real replications of experimental observations. So, we must use the experimental data as a benchmark to calculate the CL and CD when you design a wind turbine. So, this is all about these problems. Thank you for your attention. With this, I conclude this lecture.